So in this example, we've got the same mass and the same force, but the force is in the opposite direction, but the direction of displacement is in the same direction as before. It's opposite to the force. Now, work done is not a vector quantity. It doesn't have a direction, but it is scalar, and it can be positive or negative work done. So unlike kinetic energy, remember kinetic energy, the equation's a half mv squared. You're squaring that velocity, and therefore this is always going to be positive. It's a positive scalar. However, when you're talking about work done by a force, it is scalar, but it could be positive or negative. So the equation, when you're using the equation work done is force times distance, or force times change in displacement. Let's just use force times displacement. Then we have to be careful about the directions of these. And so we've got force. In this case, our force is in the negative direction. So it's going to be negative 50 times displacement of 10 meters times 10, which is equal to negative 500 joules. So same as before, but this time it's negative. Now, you've got to think about what situation could arise in which the object is going in the opposite direction as from the force, if only that force is acting. Of course, there could be another force pushing it, but let's say this is the net force. In what situations could that arise? We've got no other forces. Well, what could happen is it could have an initial kinetic energy here, and this force is slowing this object down. So it's the force that causes a deceleration. So let's just do an example with some numbers. So for example, the question might say something like, for initial velocity is equal to, say, 20 meters per second. It might ask you, what's the speed after displacement of 10 meters to right with force as above. So in this case, the initial velocity would be, or the initial kinetic energy would be a half, let's say, Ek naught. So initial kinetic energy, Ek naught, is equal to half mv squared, which is a half times 10 times, what did I say, v naught is 20. 20 squared, 400, 4 times 5, 2000, I think. Let's just double check it. 0.5 times 10 times 20 squared, 2000. Which is joules. So that's the initial energy. Okay, and then at the end, so Ek naught, well, it's just going to be the, kinetic energy at the end, so Ek1. It's just going to be Ak naught plus the work done by the force, so plus U. And so in this case, it's going to be 2000 joules, take away 500 joules. So you've got a negative work done by the force. So it's removing energy from that object. So negative 500, which is equal to 1500. So an Ek1, so the kinetic energy in the final position is equal to a half v1 squared. This should really be v naught squared, which must be equal to 1500. Therefore, v1 is equal to, so it's going to be 2, just moving everything across the other side, 2 times 1500 divided by m, and then we're going to have to take the square root. Now, m was 10 kilograms. 10 kilograms. Then you're going to take the square root of that. So root 2 times 1500 divided by 10, which is equal to 17.3 meters per second, is velocity at end. Okay, so this idea of work done by a force could be positive or negative. If the work done, and it's negative when these two vectors, the delta S and the F, are in opposite directions, you're going to get a negative work done. Work done is a scalar, but it can be positive or negative, unlike kinetic energy, which can only be positive. Also a scalar, but it can only be positive. And then we can, so what that means is when you get a negative work done, that means this force, so you're doing work against this force, or this force is taking energy from this object, so it's negative. And so therefore we're going to get, if we want, we can use that fact, so we could calculate the energy if this object has some velocity at the start, which it would have to be moving against this force, would have to have some initial velocity. And so if it's got a velocity at the start, we can calculate the initial kinetic energy. Then we can use the fact that it's doing work against this force. So you're going to subtract the work done by the force, or you're going to you're going to add the work done by the force, but it's negative. So you're subtracting that 500. And then you can use the equation for kinetic energy again to figure out the velocity at the end. Now you could have done the same thing using the equation of motion. And so what we could have done is we could have figured out the acceleration or deceleration associated with this force, negative acceleration, or it was a deceleration. Let's just do that to show that we get the same answer. And so we can figure out for this one, the acceleration is going to be the force divided by the mass, which would be, what was the force? 50 divided by, so 50 divided by, the mass was 10, which is equal to 5 meters per second squared. Then we could use the formula, so V at displacement s squared is equal to initial velocity squared plus 2a s minus s naught. Just take s naught as 0. So this would be 20 squared minus 2 times 5 times the displacement was 10 meters. So therefore V is equal to the square root of all that. 400, take away 100, 2 times 5, 10 times 100. Squared, sorry, so square root 20 squared minus 2 times 5 times 10 is also equal to 17.3 meters per second. Okay, so you can get the same answer in an alternative way. And that'll often be the case when we're working with these energies. Just using energy and work is another way to solve problems. And sometimes it's a lot quicker than using the equations of motion. In this case, it's not much different, but sometimes it's a lot quicker. Okay, let's have a look at some more examples and probably start looking at, this is an example of thinking about conservation of energy. We've got one more energy type to think of, that's potential energy. So we'll have a quick look at that, and then we'll look at conservation of energy and how we use that to solve problems. Oh, we also need to think about work done by friction. But all of those things, we'll have a look at those. See you in the next example.